So this is a rat. This rat has had its spinal cord completely cut in two. Then we put in 1 drop of a polyethylene glycol solution of graphene nanoribbons. Remember I told you that we made those graphene nanoribbons by splitting open carbon nanotubes? Put 1 drop in the gap there, and then after 2 weeks, the rat gets up and starts walking. This is the Jerry Seinfeld strategy for really becoming good at thinking up inventions. So it says top performers in every field, athletes, musicians, CEOs, artists, they're more consistent than their peers. More consistent. So what Jerry Seinfeld did, you might not know. Do you know who Jerry Seinfeld is? All right, so you don't know. Okay. All right, so he's a great comedian, but he's more my generation than your generation. And so, but anyway, he's just considered one of the world's greatest comedians. Did I say musician? Comedian. And what he did is he would force himself every day to write jokes. I mean, something like 10 jokes he had to come up with from scratch every day. And he would just start recording this on a calendar. And he just did this every day. So he can really think of jokes on the fly. So what I want you to do, I was thinking, the way I'm going to test you is I really want you to be creative. If you're creative, no matter what field you are in, you are going to excel more than the other person if you learn to be creative. And creativity isn't something that, well, it might be something you're born with, but you can also move yourself into it by forcing yourself to think of ideas all the time. You force yourself to think of new ideas all the time, and that will help you to be more creative. So every week you're going to submit an invention. You're going to invent something every week. This has to be your own idea. You have to think of something, and something hitherto unknown or done in an inferior way. For example, you might think of a better paperclip. Come up with a design of a paperclip that's different. Now, I'm just throwing out an example. So it's not like you have to design a spaceship. Just even a paperclip or a superior flower pot. I mean, what's to a flower pot? Well, maybe think of something that would give you a nice feature in a flower pot. I'm just thinking randomly. Maybe a flower pot that had some water supply that could drip in at a certain time. Those things are probably known. If you check on Amazon, you probably find something like that. But you see what I'm thinking about. It's something simple. And over the semester, you're going to get better and better at thinking up ideas. Or a new clutch for a car. So you say, well, it used to be we had stick shifts. Now they don't have those too often anymore in the U.S. But other people have designed clutches like based on ferrofluids. Ferrofluids are these fluids that have ferromagnetic iron. They have iron particles in them, and then when you put a magnetic field across it, what happens is all of these align and the fluid viscosity goes up dramatically, and that is then the engagement for the clutch. So it's very different than a normal clutch where you're actually thrusting something into position. It's when you move this, the ferrofluid moves this. So they're advanced clutches. Or you might think of a new app. You don't have to make the app. You don't have to show me your phone. Hey, look what you don't have to do that. Just think of an app. Just say, it'd be great to have an app that did such and such. And you have to search around and make sure that that app is not known. And so, for example, there was one kid, and he developed an app. Instead of swiping, you could just do this. And just that motion made it a little, so you didn't even have to move your thumb. Why wear out your thumb when you really don't have to? You just do that. So think of a new app or something like that. So, and then you have to answer 2 questions to tell me something. Just what is it? This is a paperclip. And what problem does it solve that my paperclip doesn't do? Why is it a better paperclip? Or, this is a combination paperclip/staple. Or something. It's a staple that's easily removable, like a paperclip is removed. And I'm just thinking crazy. But I want you to be creative, because what you're going to see in this class is all the different technologies that we came up with in my research group, which means that often it's my students, and then they kindly put my name on the paper. But it's the different technologies that we came up with, and you say, how'd you come up with that? It's the Jerry Seinfeld approach. You just keep thinking up ideas. Just keep thinking up ideas. And that's the nice thing about a field like chemistry, because in chemistry you can try things very rapidly. It's not like in some big physics experiment where you got to use an accelerator and you got to plan for years and to try one experiment. Chemistry, you can just go in the lab today. You think up something and go and try it. And it's really fast, and our analytical tools can be really fast to figure out, did it work? And then, so what is it, and what problem does it solve, or what new thing does it do? Why does anyone care? Basically, why does anyone care? And let me give you an example of something that's interesting that I purchased myself recently on Amazon, that are very simple things that people have thought of. And so look at that. Do you know what that is? I bought that on Amazon. Do you know what that is? You don't know, do you? Well, because it doesn't have a scale bar. You don't know if that's, a sleeve for my arm, or you don't know what it is. But as soon as I put a scale bar there, that's 1 centimeter. That arrow, that double-headed arrow is 1 centimeter. So these are relatively small. Why would I buy that? Has anyone ever gone bass fishing? Anyone here ever bass fish? One person? Two. In the state of Texas? Have you ever gone bass fishing and caught a lot of fish? Yeah. Do you remember anything that happens to your thumb after a while? What happens to your thumb? It gets cuts all over it because you go to pick up the bass and you take it by its mouth and so that you can extract the hook. And then after a few fish that you've done it with, they have these really sharp teeth, and it scratches right about here on your thumb. And after a few fish, your thumb is just sliced. So you can put these things over your thumb, and it doesn't bother you while you're fishing, and you just grab that fish and it just never goes through that. That's not a bad invention, right? And so you buy it for $6, you get 3 of them in the package. That's all I'm talking about. Isn't that a simple invention? And now these people are making money. And you can sell it on Amazon, and Amazon gets 20% of every sale, and they do the delivery, so and so that's kind of the way it works. Look at something else I bought. So I bought that bottle. Did you ever try to have a protein shake and you're shaking for 20 minutes to really get this thing mixed up? You've done that? It's just kind of a pain in the neck, isn't it? And so here, I was thinking somebody must have thought of a little electric thing, and they have this, and you just charge this up through a USB port, and you push the button, and it goes for 30 seconds, and the thing is it's equivalent to probably shaking this for 2 hours. It's just totally mixed in 30 seconds. The thing just gives you this great vortex. That's a simple invention. You say, I'm going to invent a cup, for my, what bothers me in life? Well, it's shaking up this protein shake, making up this protein drink. This is what bothers me. Okay, well, how am I going to solve this? Well, put a little electric motor, and it's all kind of sealed up, and so it's very easy. And that's a great invention. And I don't know how many of those they sell every day, but it's not a bad invention. So just going through life, if you talk to Elon Musk, why did Elon Musk buy Twitter? He just had $40 billion burning a hole in his pocket. I mean, why did he buy it? He said because he was a Twitter user. He was one of the biggest users of Twitter. I mean, and just used it all the time. So he really understood the technology, and he understood the problems with it. And he thought, and he's a big believer in investing in things that you use, investing in things that are of interest to you, because then you're a participant in it, and you know how to improve it. So just go through your life and think, wow, this is a pain. I wish this were different. All right, how do you wish it were different? And then you start thinking up an idea. But this is now going to force you every week, the Jerry Seinfeld approach. He thought of jokes. Every day he had to write 10 jokes. And every week you're going to be thinking. So this is something you don't have to be sitting, in the room, in your college room there. You don't have to go to the library and say, I'm going to figure this thing out. Just walk around. Just walk around. And you can think of this, and what I want you to get in this habit of doing is, as you're walking around campus, as you're going places, just think of what can I invent? What can I invent? Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. Here's another thing I recently got. It just plugs in the wall, and it's just an outlet that plugs into the wall, but it has the USB ports already in it, and it has a surge protector, all in one. You get everything all in one in this one outlet. Very simple inventions. Now, you have to conceive of this on your own per the honor code. Now, once you've thought of it, you could go to an expert and say, could this thing work? Could something like this happen? You might say, I invent a transporter where I'll dematerialize and then be in London in 4 seconds. Right? That's a really cool invention, but speak to some experts and they'll say, we don't have technology that can make that happen. But when you're doing something like this cup right here, we know that there's electric motors that can be charged. So you don't need to go to an expert. You're enough of an expert that you know that there's electric motors out there. So that sort of thing can be made. But you might need an expert. You might go up to a chemist and say, could a molecule like this be made fairly easily? In a few months, could something like this be synthesized that would do such and such? So you can ask your experts like this, but I want the basic idea to be your own. This is an overview of what the semester is going to be like, the types of things we're going to talk about. These are things that have come out of my own lab. And what I'm going to do is when I talk about these things, I'm going to also tell you about the companies that we've started around these things. And I'm going to tell you about the people behind this so that it's not just, wow, this is an amazing thing. That you'll learn some of the people behind this and the saga of what was happening at the time. So throughout my career, we've developed a lot of things, but these are things that have all been developed in the last 10 years or so. Now, some of them actually date back even more than that, but these are things, we're going to go into the details of this. So for example, this is laser-induced graphene, where we can turn any carbon material into graphene. If you don't know what graphene is, you will by next week. And you can turn it into graphene. It's single atomic sheets of graphite. You say, well, you need this elaborate laser. No, you don't. Every machine shop has this laser. There's like 6 or 8 of them on this campus, maybe even more than that. Every machine shop has 1 or 2, and they're laser cutters. You scribe things with it, and anything that's plastic, anything that's carbon, wood, anything that's carbon. This is a piece of polyimide, it's a piece of plastic. This is bread. We're not dropping graphene onto the bread. Wherever the laser hits, it turns the carbon, in this case, carbohydrate strands of the bread, it turns it into graphene. So it heats it, it carbonizes, it blows out all the other atoms, and that's because carbon doesn't boil until 3,800, 4,000 Kelvin, whereas other elements, even silicon, oxygen, they're coming out about 2,600, 2,800 Kelvin. So all these other elements fly out and only carbon is left. And it thermodynamically rearranges to the most stable material, and that's graphene. The most stable carbon material is these sheet-like structures. It's not diamond. This is a coconut. We made a pattern on it and turned it into a supercapacitor. So a supercapacitor is like a battery, but it charges much faster. Doesn't hold as much energy as a battery will, but it charges much faster. This is carbon nanotubes that we split open chemically. We split it open chemically. And I'll tell you about the guy. When we're talking about laser-induced graphene, I'll tell you about the guy who discovered it and how he discovered it. This was serendipitous. But as soon as he saw it, he realized the value of that. And we got bunches of papers on this, and this will spawn several companies. This one, it's graphene nanoribbons were made by splitting open a carbon nanotube. So if you have a tube and you split across here, it would form a ribbon. And then I'll show you in a minute what we're doing with those things. This is a computer memory. This is a memory based on silicon oxide. And you say silicon oxide is a dielectric. It's actually a switch. We turn it into a switch. And again, this was an observation by a student of mine. This was an observation by a student. This was an observation by a student. And then we capitalized it. on it. And so this is in a company. This is going to spawn numerous companies. This is now a public company. So we'll talk more about that. But it's a switching device, and it's memory in a computer. This here is we've developed a material, a drug, a nanoparticle drug that's being used for traumatic brain injury and stroke. Stroke is the #1 disabler of older adults. Traumatic brain injury is the #1 disabler of younger adults. Skateboards, bicycles, you walk on a sidewalk out here, you take your life in your hands with all those scooters going by. And you say, well, it won't, scooter isn't really going to hurt you. If your head slams on the ground, you got a traumatic brain injury. That's the #1 disabler of young adults. And this was based on a nanoparticle. A nanoparticle, we developed it, and it was originally based on research that we were doing to make carbon fibers. And then we used it in the oil field to help to design a system to pull oil out of the ground. And then we modified it and made it into a drug. And so you get these ideas for one thing, and then you start applying it in other areas. This is why it's really good to read broadly. There's these people, we'll probably talk about this later on, called T people. T people, you know what a T person is? Like the letter T. I was visiting 3M Corporation, an amazing company. And what they did is they studied how much a person contributed to the company. In other words, for every dollar that we spend on one of our researchers, how many dollars do they bring back to the company? That's how you make an assessment. Are we really bringing value here? Are we spending more money on people than what they're generating? And at 3M, which is a very innovative chemical company, they plotted this out, and most of the people brought in $5 for every dollar invested in them. So if you look at their salary, their retirement, their benefits, for every dollar invested, they're bringing $5 into the company. And the way they tracked this is they saw how much did this person, they looked at their patent claims, and they knew how much money each of these patent claims was bringing in business, and who contributed to that patent claim, and that's how they tracked it back to person's contribution. However, there was a small number of people in the company. So some people were less than $5, the median was $5, and then out here, there were some people that were bringing in $500 for every dollar invested in them. Think about that. That means that you hire this one person, they're going to make as much money for you as 100 other people. That's pretty amazing, isn't it? And so they tracked, what is it about these people? What is it about them? And there's only a handful of them. So they studied these people. And what they realized is they ended up calling it T people, meaning that they were deeply trained in something. Like they usually had a PhD in some field, so they had some depth of understanding, but they were extremely broad in what they were able to do. So in other words, they could speak to biologists, they could speak to chemists, they could speak to engineers, and they could begin to relate. This is why even reading on something like Reddit, something that just expands your mind beyond just your absolute field, because each of you is going to choose some field, and you're going to have to get a deep understanding in that. But then when you study broadly, then you begin to make these relations, these cross points. And that's why I said it at this point, because we developed this particle for making better fibers, and we applied it to oil field, and then when we were thinking of another project, maybe these would be great reactive oxygen species traps, and they were. And so we developed it into a drug. So you make these relations across all these fields. So like now in my career, my brain doesn't work as fast as a 25-year-old brain anymore. And you can see it. You can see it. You just watch you guys. You go down steps, and I used to go down steps like that. And now I usually grab a banister and I go down a little bit more slowly. So your neurons are firing much more quickly when you're young. But you don't have the breadth of what I've seen over my career. I've just seen so much. Right away I see something, I say, oh, we can apply that to this. Here's an important question. Why would anyone believe that a man named Jesus died and rose from the dead? If you don't believe in the physical resurrection of Jesus Christ, send an email to tour@drjamestour.org and we'll set up a meeting, and I will tell you about why I embrace the resurrection of Jesus Christ. So this is carbon nanotubes growing seamlessly from graphene. So a sheet of graphene and carbon nanotubes growing seamlessly from that. And so when we got this, the student measured the surface area of this, and it was like 3,000 meters squared per gram of material. So think of having a gram of material. A gram of material is like, a portion of a penny, a gram of material. And think of having a surface area of 3,000 square meters. I mean, that's a lot. As soon as I saw that, I said, this is an electrode. This is an electrode. Imagine in a tiny little electrode how much surface area there is, how much information you can have going. In this case, we're going to use an electrode, so how many electrons we could have transporting through this. And so this was the genesis then of building batteries, and that's now a battery company in North Houston, Zeta Energy, and it's a battery company, and they've raised, like $40 million to this point, and they're building a prototype plant. They're sending out prototype batteries now. People like Tesla, people like Apple, they don't make batteries, they just buy batteries from battery manufacturers. So you make a lot of batteries and you send them out to the different people that make batteries. This is graphene quantum dots. Graphene quantum dots. When we started on this work, graphene quantum dots were $1 million per kilogram. So a kilogram of material, 2.2 pounds, was $1 million, graphene quantum dots. So we learned how to make them from coal, like you dig out of the ground, coal. Coal is $60 per ton. $60 per ton in one step, 25% yield. So think about those economics. One step, 25% yield, $60 per ton, $1 million per kilogram. That's pretty interesting, right? Of course, the price of these came down, and so this is in a public company. So we started a company which has gone public on that. This is where we take plastic waste and convert it into a material that can absorb CO2. So did you know plastic waste is a problem in the world? And so you can take plastic waste and convert it into a material that sucks up CO2. So you take one problem and you use it to solve another problem. We'll talk about the genesis of all of this. This is our nanocars. So we built these little cars. They have 4 wheels, independently rotating axles. This motor spins. If you shine a light on it, this little molecular motor will spin at 3 million rotations per second. And it will move this car across this surface when it spins. So this is looking at it much more slowly than that motor normally turns. It's 3 million rotations per second. And it will move a car across a surface. Now, these cars we just thermally heated this and the car started moving. So here's a car pointing and it's moving across this surface. And so you can see a car moving. And so these are nanocars. And then we just took the motors and hooked peptides on these to recognize certain cell surfaces. So there are these motors. The motors were known. They were called Feringa motors. We just built them into a car, right? We had a lot of fun with cars for many years. We'll talk about that. And then we used the motors to drill into cells. The motors by itself just drill into a cell and pop holes in it. So this is a bacterium, and you see the whole cell wall is just gone. And its guts are just spewing out. So you can drill into a cell with these things and kill them. This is a synthesis of graphene, bulk scale synthesis, where you take 2 electrodes, you put a high voltage and a high current across this thing, and when you do this, it'll take all those carbon atoms and rearrange them. So you just take something like coal. You can do it with any sort of carbon, and you just heat it up. But you do it really quickly by just pouring the energy in electrically. So we put a high voltage, a high current through this, and it just turns into graphene in bulk. This one was making patterns of graphene. This is for patterning. This is a different business. This is making bulk graphene. This is in a company we started, and they're scaling it up now. And so this little machine here was an automated system that we built during the COVID shutdown. So we were out of our labs from March for 2.5 months, March until somewhere in the summertime. And I bought some 3D printers and sent them home with the graduate students. And they bought the little motors from Amazon and from eBay, and they built that thing. And that allowed us to build an automated system that would do this, where these two electrons come in and you can see the thing flashing. And then now this is going to be just doing a ton scale right now in the company, a ton per day. So you really scale it up. We'll talk about why graphene is really important, and then applying that same technology of very rapid heating, because the reason why many furnace procedures are very high energy is because you heat a whole furnace structure. Here you're driving all the energy into the system, so we can use about $30 in electricity per ton of graphene being made. Per ton, $30 of electricity. Because all the energy goes into the material, it's not heating a big furnace. And the temperature, this rises to about 3,000 Kelvin, roughly 3,000 centigrade, this rises to. And so very rapidly, within 100 milliseconds, it's at 3,000 Kelvin. And then it cools, so it heats at 10 to the 5th Kelvin per second, cools at 10 to the 4th Kelvin per second. So it's just a very rapid boom, spike of heat, and then it's done. And so this is how it is being scaled up. And then we applied that to all of these things. This is a mountain of fly ash, which is we have mountains of it in this country. It's the leftover that's left over after burning coal. It's the inorganic. And so you can heat that up and you can get out all the heavy metals and the rare earth elements. And we'll talk all about this, how we're using this to recycle, to upcycle. These are printed circuit boards. Every time you save something to the cloud, that is going to on some printed circuit board somewhere, probably somewhere in Texas. All of this is being stored. And those circuit boards are replaced about every 3 years. And there's mountains of circuit boards. And that's toxic waste. So every time you save something to the cloud, think about that. You're generating toxic waste. So that's toxic waste. And so those printed circuit boards are. So we're learning how to get the precious metals out of that and the useful metals out of that so that you don't have to do mining anymore. We're remediating soil this way. This is red mud. It's the leftover after making aluminum. And it's another toxic waste, and we're detoxifying the waste. And we're recycling all the battery metals, both the anodes and the cathode, the graphite and the cathodes. And we'll talk about the chemistry on that. But this just kind of gives you an overview of the types of things we're going to be looking at for the semester in a little more detail. All right? And I'm going to give you the names of the people and the stories behind what was going on. All right, so this is a rat. This rat has had its spinal cord completely cut in two. Now, we don't do the animal studies. That was done by somebody else. So this spinal cord was completely cut in two at the base of the neck. And then we put in 1 drop of a polyethylene glycol solution of graphene nanoribbons. Remember I told you that we made those graphene nanoribbons by splitting open carbon nanotubes? Put 1 drop in the gap there, and then after 2 weeks, the rat gets up and starts walking. Has anybody seen a YouTube short on that? Yeah. Okay, yeah, we made a YouTube short on this, and it's got like 5 million views. And then after 3 weeks, she's doing wonderfully. And so you see there, there she is after 3 weeks, scored a 19 out of 21 on mobility scale after 3 weeks. 21's optimal mobility. And she scored 19 after 3 weeks. That is with a totally cut in two spinal cord. It's interesting, you can take these graphene nanoribbons now, and you put them in this gap. So you've cut the spinal cord, now it's in 2 pieces. And this is just a solution with the graphene nanoribbons. And you do this with the spinal cord. You just open the gap and touch it back together. In doing that, you've gotten these graphene nanoribbons to now align. It's called shear flow. Logs are in a lake, all disordered. As soon as they start going down the river, what happens? They all align with the river. That's shear flow, all right? So all the logs align with the river. Same with the graphene nanoribbons. They will align now just by doing this in that polymer gel that's there, and now they've aligned. And now when the neurons start growing, they grow from top to bottom and bottom to top. But normally, they just miss each other. So it's like ships in the night, and then they never reconnect. But here you have the graphene nanoribbons, and we had known from a bunch of other studies that the graphene, that cells, neuronal cells, like to grow on graphene. Well, why do they like to grow on graphene? Because graphene is conductive, and neurons like to grow on conductive substrates. It's because they're always sending out electrical pulses. And so what happens is now you have all these billions of them in there, in this gap. And so they'll start growing along the graphene nanoribbon. And some are growing from the bottom and some are growing from the top. And now they're growing along these highways. And now they run into each other and then they reconnect. And so the first 2 weeks, the rat was just sitting there just kicking around because the whole brain has to remap. Because what was the connection to the little toe is no longer the connection to the little toe, it's to the little finger now, or whatever. All the connections have to remap. But just like our brains mapped it one time, it remapped it again. So this is why a little child, a newborn, you give them food, they don't know what to do with it. They don't even know how to hold it. And then when they learn to hold it, they stick it in their ear. They don't know how to direct it to their mouth, but after it's mapped, they've learned this thing and knows exactly where to put the food. The brain has mapped this. So the brain has enough plasticity that it can just remap the connections. That's what we're talking about. We remap these connections. So the National Nanotechnology Initiative, sort of like how nanotechnology came about. This is Richard Feynman. He won the 1965 Nobel Prize in Physics. He gave a lecture in 1959 and then wrote a paper about it in 1960 called There's Plenty of Room at the Bottom. So this is a PDF article that you can get online if you just did Plenty of Room at the Bottom, Richard Feynman. This is a guy who would think differently than everybody. He was an amazing guy. Some people don't like him because he was a little cocky, but that doesn't bother me a bit. I mean, he deserved to be cocky. I mean, he thought of so many things. Have any of you ever met a fighter pilot? Guys who fly jets and drop bombs and shoot things. Okay, if you ever meet a fighter pilot, I've met many of them. They're all cocky. And you want somebody like that in your fighter jets. I mean, that's just, you don't want people who are timid. You want people who are really out there and going. So this guy was amazing, wasn't timid at all. And you can watch bunches of videos of him on the internet. He died, I don't know, 25 years ago, no more than that. Maybe 30 years ago, something like that. But amazingly colorful guy. And he talked about how at really small scales, there's all these things that you can do, and we never really work at these scales. Now, fundamentally, when you're synthesizing molecules, you're working at those scales fundamentally, but he said there's so much other science that can be done at these small scales. So he has this lecture and this paper, There's Plenty of Room at the Bottom. And he wrote several books, but this book, Surely You're Joking, Mr. Feynman. And so the foreword is written by Bill Gates. This guy was amazing. If you ever just want to have a grand time reading a book, this would be one of those. It's just a lot of fun to see all the different things that he did. Just an amazing guy. So he was a young guy during the Manhattan Project when they were making the nuclear bomb. Did anybody see that recent movie? What's it called? Oppenheimer. Did anybody see Oppenheimer? Do you remember a guy playing the bongos? Yeah, there was a couple times there was a guy in the back playing the bongos. That's him. He loved playing the bongos. He was just a young guy during the Manhattan Project. And so he's also the guy, remember there was I think it was the Challenger disaster. There was one 40 years ago. One of the space shuttle blew up on launch. They had like a school teacher in there, and there was an astronaut from Israel and it blew up shortly after launch. And he was the guy who figured out what happened, like almost instantly, because it was a very cold day that day. And so he looked at the rubber seals and he just stuck it in cold water. And then he took the rubber seal, it did this and just cracked apart. The rubber seals were never made to operate at sub-zero temperature. And it was just anyway, sharp guy. Okay, so he had this plenty of room at the bottom, but then Mikhail Rocco, goes by Michael Rocco, he was at the NSF and he said, let's build a program around this nanotechnology, because Rick Smalley, who was here at Rice, Rick Smalley passed away in 2005. He won the 1996 Nobel Prize for his discovery of Buckminster fullerene, C60. He, along with Bob Curl, who just passed away last year, and also Harold Kroto, who passed away about 3 years ago, who was from the UK here at Rice visiting when the discovery was made. Rick and I were good friends, and so Rick was really pushing this thing of nanotechnology because he had just discovered C60. Michael Rocco said, let's have a program, a big national program around developing nanotechnology. Also, on the Hill was Neil Lane. Has anyone ever met Neil Lane? This is Neil Lane and Bill Clinton. Neil Lane is a professor here. He's now in the Jones School and in public policy, but he was a physicist at Rice, and then he became provost and then maybe president in Colorado, and then he was selected to be the White House, then he became head of the NSF, head of the National Science Foundation. Then Bill Clinton chose him to be White House science advisor. He pushed this whole idea of having a national nanotechnology initiative with Bill Clinton. He pushed that with Bill Clinton. Mikhail Rocco proposed this initiative in 1999, and he presented it to the White House and the Clinton administration. Neil Lane, who's here, who's a professor here, you know, what I've encouraged students to do in past years is get to know Neil Lane. There are people you have access to as a student that you will not have access to when you're not a student. You say, why? Because you get contacted all the time by people that want to get together with you, and you just don't have enough time. But if you're a student, professors often make time for you. Okay, you want to get together? Okay. I think you should contact Neil Lane. This guy has seen science from being a young professor to running the National Science Foundation to being in the White House there. And just say, I heard about you, I want to take you to lunch. And just say, if you're busy this week, how about next week? If you're busy next week, how about the week after? And just push it. He'll have lunch with you and take him to Brockstein Pavilion and spend $10 and have lunch with him. If you don't have $10, come to me, I'll give you $10 so you can have lunch with Neil Lane at Brockstein Pavilion. Because it can mean that much to your career. When you're applying for a job, if you've gotten to know Neil Lane, if Neil Lane writes you a letter, it has an enormous impact. There are certain people that if you get to know as students, you leverage that. One of the things that people don't appreciate when they're young is the power of contacts. We used to call it a Rolodex. Students don't know what Rolodexes are. They used to do these things that with all your cards in it of the people you have met. And then they had electric Rolodexes that you didn't have to turn it by hand. You push a button and it would turn. Now it's all, of course, computerized. But it was called a Rolodex. And having these relationships with people is what opens the door for you again and again. So you want to get to know as many influential people as you can get to know. Your companions here are going to be influential someday. So the more people you know as a student, the more you can leverage that in the future. If you go, for example, to Harvard Business School, you're going to meet a lot of people that have already been out for 5 or 7 or 10 years, and now they're back at Harvard Business. These are like top dogs there. And you get to know them, and that's why when you graduate from Harvard Business School, you have all these people, because there's 900 people per class at Harvard Business School. So you get 2 years of 900 people. So you get to know a lot of people. It's the connections. It's the same in science. It's the same in engineering. Get to know these people. So get to know Neil Lane, and he can tell you some Bill Clinton stories. If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.